So 8.1 to 8.3 is just the construction of probability. So fundamentally, when it comes down to any of these problems, you're thinking of some probability of an event is equal to the sample size, sorry, of your event over the sample size, sorry, the cardinality of your events, and then the cardinality of your sample size. Or as I like to prefer, is the number of E over the number of S, or even better for me personally, what I desire over the total. Okay. If I want to roll a 6, well, how many ways can I do that? 1. How many ways are there to roll anything? 6. So 1 out of 6, right? So that's the fundamental rule of probability. It's just figuring out what you have for the total and then what you want or desire. So we'll start with the first homework question, or sorry, review question. So consider an experiment where a fair coin is flipped 3 times. Let A represent the event that heads comes up at most 2 times in 3 flips. Find the probability of A, right? Now, there are many ways to do this problem. There are more elegant or kind of like clever ways of doing it. But always remember, you can just go back to the basics. What do you want and how much do you have total? Okay. So step number 1 is formula. So the probability, right? And I always tell students, just write out what it says. I want 2 heads. So represent an event that comes up at most 2. So at most 2 heads. Okay. That's what I want. Now, again, there's another way of writing this. I could write the probability of 0, 1, or 2 heads, right? Or the probability of less than 3 heads, right? There's so many ways that you can write this, but be the most obvious for yourself. And so what that means is I need to find the number of, at most, 2 heads over the total. Okay? That's all I got to find. So then step 2 is to find the sets and cardinality. Okay. So A is going to be equal to, so at most 2 heads, that's really just A because they said A right there. So let's just write down what that would look like. Actually, what I would recommend you do is write down everything first. Always find the total. So I would do the total first. So if I flip 3 coins, I can get heads, heads, heads. I can get heads, heads, tails. I can get heads, tails, tails. I can get tails, heads, tails. I can get tails, tails, heads. I can get, what else do I got? Tails, tails. See, 1, 2, 3, 4, 5. So heads, 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 heads. I forgot. Heads, tail, heads. There we go. And I'm missing one more. Do I have heads, heads, tails? And we got tails, tails, tails. 1, 2, 3, 4, 5, 6, 7. I'm just missing one more. I'm trying to figure out which one it is. I got the heads, heads, tails. Do I have tails, heads, heads? No, I do not. There we go. So I have 8, right? Now, if you use some of the lessons that we've learned in chapter 7, you could also do it this way. Or you could be like, I got 1 coin, 1 coin, 1 coin. So I have 3 coins. I have 2 options, 2 options, 2 options. And I have 8. Because if you count that up, it's 8. So this is an example of if you feel comfortable with combinations, permutations, and all of that, you can use that to your advantage. This is a problem where this is possible. But if you're not comfortable with that, then you can just write it all out and you can brute force it sometimes, right? And that's okay. Sometimes one way is easier for some versus the other. And then, so they say at most 2 heads, right? So 0 heads is okay. 1 head is okay, and then 2 is okay. So 0, 1, or 2. So I want 0 heads, so that would be tails, tails, tails. I want that one, tails, tails, heads. 2 heads right here. So basically, as I'm looking at this, it's all of them except one. The very first one. Okay. Which is the heads, heads, heads. So only one of them doesn't satisfy what I said earlier, at most 2. Okay. And then step 3 is to plug in. So the probability of at most 2 is equal to, right? So actually, let me write this down. So then this means the cardinality of A is equal to 7. The cardinality of S is equal to 8. So 7 over 8. And that's my answer, 7/8. Now, if you want to be super clever, like you can do this. I don't recommend that you do this unless like you feel really, really comfortable. But there is a cheap way of doing it, and it's using the complement rule, where the probability of at most 2 is equal to 1 minus the probability of the opposite, which is more than 2, which would be 3, right? So then it would be 1 minus the probability of you getting 3 heads, which is the opposite. And so how many ways can you get 3 heads? Well, that would be 1 minus 1 over 8, which is 7/8, right? Like that's the cheap way of doing it. And it's probably the best in this case. But for you, pick whichever method makes the most sense to you and then just do that. Don't try to use any kind of tricks because sometimes those tricks will be not your friend. Okay. So, all right, next question that we're going to do is the dice problem. So very similar in this question or in this style. So consider the experiment where 2 fair distinguishable dice are rolled. Let B represent the event that the sum of the 2 numbers is 5. Find the probability of B. So essentially they're asking, find the probability of rolling a 5. Okay. So step 1 is, what's your formula? Well, the probability of a rolling a 5 is equal to the number of 5s over the total. Okay. The number of 5s over the total. Now, a key word here that you have to pay attention to, and honestly, I don't think you have to worry about the other case because they don't really like to do it. Distinguishable. That means each dice is different. You can tell the difference between them. If it was indistinguishable, this would make the problem a little bit more interesting because you'd have to basically get rid of any duplicates, but you don't have to worry about that. Okay. So we have that. Step 2 is to find the cardinality of B and total. Okay. So B is equal to rolling a 5, which is going to be equal to, so how many ways can I roll a dice? Like a 1-4, a 2-3, and then a 3-2, and then a 4-1, right? So there's 4 ways I can do that. 1-4, 2-3, 3-2, 4-1, right? And remember, if you want to, you can think of like the first die being red and the second die being blue. So 2-3 and 3-2 are not the same thing. Okay, they are different. And then the cardinality of that, okay, and again, I'll write this in a more traditional way, is going to be 1, 2, 3, 4. And then for S, okay, it's going to be 1, 1, 1, 2, ... 6, 6. But you should just know this, okay? So the cardinality of rolling 2 dice is always 36, okay? And again, the more proper way of saying this is I have 2 die. I have six options, and then 36. So first die, and then second die, like that. Any questions on that? And then step 3 is to plug in. So the probability of B, which is rolling a 5, is going to be n of B over n of S, which is 4 over 36, which is 1/9, right? And you should always get nice fractions for all of your answers. So the probability of OR, so the probability of A or B is defined as the probability of A or B equal to the probability of A plus the probability of B minus the probability of A and B. So it's basically using the cardinality rule that we learned previously, but expanding it to the probability. And the reason this formula works is because if you take the cardinality and then divide everything by the total, it just becomes a probability, right? And so the first question that we can easily ask you is, okay, just use the formula. So I give you enough information, can you find the missing one? And then after that, we're going to do the Venn diagram problem, right? So step 1 is to write down the formula. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. And then in this case, step 2 is just plug in. So they told me it's 0.6, 0.3. I don't know what P of B is because they're asking me to find it. And then this is 0.2. And then I just simplify. So 0.6 equals 0.1 plus P of B. And so P of B, subtract that over, is 0.5. And that's all it is, right? So from that, we can look at a different problem, which is, okay, what if I give you a Venn diagram problem? So essentially, I want you to fill out a Venn diagram. I could ask you on the exam to do that. So that is always a possibility. So let's get this right here. So a couple things to remember here. This is called the universal set, the rectangle itself. And then the first rectangle will always be whatever the first thing they describe. So 75% chance of rain in New York, 30% chance of rain in Honolulu. So this will be New York, the first circle, and then this will be Honolulu. And then from there, we start to fill out some information, right? And so I always recommend, okay, and they even tell you it has to add up to 100%. So always work inside out. So what value do they both share? Well, they say right here, there is a 10% chance that it will be in both cities, right? So that's going to be this region right here. So that's going to be 10%. So you can write it as 10% or 0.10, right? Now, this is where it gets a little tricky because you got to pay attention to this. The 75% from New York is not just this. Like, it's not this, actually. What it is the entire circle. So this is the 75%, right? It's the entire thing. So I'm going to write that down. 75% for New York is the entire circle. And just to be clear to the reader, left circle. So I must subtract 10%. to get the true New York percent. Okay. So really what I want is 75% minus 10%, and that's going to be equal to 65% or 0.65. Okay. So that's the true answer. And you really got to pay attention to that. Okay. It is a very common mistake where students will not pay attention to that, and they'll write down 75% for the circle that is the incorrect answer. Okay. So 75% minus 10% is 65. Yep. And then there it is. And then it's the same thing for Honolulu. So the 30% for Honolulu is the entire right circle. Subtract 10%. So 30% minus 10% is equal to 20% or 0.20. Okay, just like that. Now, we're almost done. So the entire box has to add up to 100%. So if you write 100% on the outside, inside box, including circles, then what is the percentage of just outside of the circles, but inside of the box? So for that, you would do 100% minus 10%. Actually, we'll just do it from biggest. 65% minus 20% minus 10. And that's going to be equal to, looks like 5%. Yep, 5%. So 0.05 is the value inside of the box. And that fills out our entire region. So you will need 4 answers for this. The 3 circle answers, and then the box itself, okay, inside of the box. And they tell you that the entire thing, if you add them all up together, it should be 100%. And then from that, you will be asked maybe 2 follow-up questions or 3 or however many they want to do. And from there, you don't even have to use any formulas. You can actually just kind of make the logical conclusion just from the information that they give you. Okay, so I'm actually going to remake the Venn diagram. That way we keep having it with us as we do these problems. So paste that right here. Okay, so this was New York, this Honolulu, this was 0.10, this was 0.65, 0.20, 0.05, and then this is 1. Okay. So the question is, what is the probability it will rain in neither of the 2 cities? So the probability of neither 2 cities. Okay. So basically they're saying, well, if it can rain in New York with the 65% chance only, or 20% chance in Honolulu only, or 10% chance of both, well, there's only one case where it rains in neither, and that's going to be this one right here. So this is the neither. I'm going to write that over here. This is the neither region. So the answer is just 0.05. Like, you don't have to use a formula. The Venn diagram does all of the work for you. Okay. So if they want your answer as a percentage, you would write it as 5%. Decimal or percentage, we will make sure that is clear on the exam. That way there's no confusion. And then the next question they might ask you is something like this. What is the probability that it will rain exactly in one city? Okay, one of the 2 cities. So again, you can use the Venn diagram here. So for exactly one of the two cities, okay, it's just basically saying the probability of New York or Honolulu only, okay? So one or the other, but it can't be both, okay? But not both, okay? So exactly one. Or you can write it as the probability of New York only plus the probability of Honolulu only. That's another way of thinking about it. So it really just depends on what interpretation sounds the best for you. But in either case, you're just saying, okay, there is a 65% chance of New York only, and then plus a 20% chance of Honolulu only. And so if you add those two together, there is an 85% chance, or 0.85. And in either case, you get the correct answer, okay? So that one's a little trickier, just because it's exactly one. If I said the probability of either of the two, then it would be the sum of all of the circles. So it would actually be 95% chance. But because of that exactly one, they make it a smidge more difficult, okay? All right, so before we do the last example from this section, I just want to remind you of the complement rule. So the probability of, we'll use A, is equal to 1 minus the probability of not A. So probability of, I don't want to say this, heads would be equal to 1 minus the probability of tails, the opposite, right? Or probability of a 5 is equal to 1 minus the probability of not 5, right? You're just doing the opposite, and that's what I want you to gain from this example. Some problems, sometimes that is actually the better way of doing it. But again, it just depends on the problem. So here's another example. So a survey conducted by the Bureau of Labor Statistics found that 67% of high school students graduating went to college, while 44% of class was working. Furthermore, 92% were either in college or working or both, okay? So then the first question would be something like this. What percentage went to college and worked at the same time, okay? So if you prefer to use a Venn diagram, you can do that for this problem. In fact, I would recommend that you use the Venn diagram, but you could also just use the formula. So step one here is define your events. So before you do the formula, make sure you define what the events are. So we'll say that E is college. Actually, let's use the letter C for college. And then W for work, right? So those are my events. If you, C means you went to college, and then W means you went to work, okay? Now, this is very important, and this is just a statistic, or sorry, a probability thing and a description. 67% of students were graduated, went to college. That 67% could also be working. The only condition that I have stated is that they're in college. So they can be doing work or not work. It just depends, right? So then step two is the formula. So the probability of college or work is equal to the probability of college plus the probability of work minus the probability of college and work, or yeah. No, we can use the word and, right? This would be union, this would be intersection, right? Don't forget that. And so step three is a plug in. So the probability of college or work, so 92% were in college, working, or both. So 92%. So 0.92 equals the probability of college. So 67%, sorry, we're in college. Actually, use this. And then let's do a different color, lavender, 67% college. So 0.67 plus, and then 44% were working. So 0.44 minus the probability of college and work. And so the problem says, what was the probability that they're at college and working at the same time? So that's what the question is asking. Just color coordinating this a little bit. That way, maybe that helps you see where the numbers come and go. Okay. And then step 3 is just solve. Sorry, step 4, solve for probability of C and W. So 0.92 is equal to 0. Sorry, not 0. 1.11 minus probability of C and W. So if I subtract this over, then I get negative 0.19. So then the probability of C and W, so college and work, is 0.19. Remember, all probabilities need to be positive and between 0 and 1. So if you got a final answer that was negative, automatically wrong, okay? And if you get an answer that's bigger than 100%, automatically wrong, because we don't define probability bigger than 100% or 1, okay? Now, again, you could do the Venn diagram if you're a Venn diagram person, which I myself am a Venn diagram person. I would have made a Venn diagram, filled it out, and then from there, just use the Venn diagram to figure out what the answer is. But if you like the formula, by all means, use the formula. There's nothing stopping you. Unless the question says, fill out the Venn diagram, then you kind of have no choice, but that's kind of the idea. All right, so what percentage went on to college but not work? So essentially, they're saying, what is the probability of college and not work, right? So probability of college and not work. So this is where I think the Venn diagram is better, because making, like, the formula isn't really designed to, modify it this way. So for this, the Venn diagram is actually a lot better. So what I would recommend you do is just make a quick Venn diagram. College, work, and then neither. So college, so they both share 19%. So from the previous problem, the probability of C and W is 0.19. So that means the inside circle, gotta make this a little bit bigger, is 0.19, just like that, okay? And so the college and work, so they told me college was 67%. So 67 minus 0.19 is equal to 4.48. And then for work, it was 44%. So 0.4 minus 0.19 And if we do that, we get 0.26, like that. And so from there, college and not work. So that would be basically this region right here. Because I don't want them to be working, just college. So then the answer is just 0.4. And there it is. That's why the Venn diagram is so nice, because you don't even have to think of a formula. You just have to find the correct part of the circle. Now, if you're wondering, how would I use that how would I do that using the formula? Well, you would do it this way. The probability of college or not work is equal to the probability of college plus the probability of not work minus the probability of college and not work. Like that. Okay. So what's the probability of going to college? Probability of going to college was 67%. What's the probability of not going to work? So the opposite of 44% would be 56%. Okay. And then what's the probability of college and not work? Well, that's what we're trying to find, right? And then what's the probability of college or not work, right? So I'd have to figure out what that is. And so college or not work would be 67%. Okay. So 67% for the college. And then for not work, that would be whatever the outside would be. So you already kind of see you're running into an issue of like, well, now I have to figure out college or not work. And so that's what makes this a little bit more challenging, is now I have to figure out what that is. And if I look at the Venn diagram, I could figure out what that is. It would be, let me add that up real quick. Uh, 0.93. So that would be 0.07. So add 0.07 to that, which would be 0.74. And then probability of college and not work, like that. And then from there, I would just solve for the one that's missing. So if I add these together, I get 0.67 plus 0.56. So 0.67 plus 0.56, which would be 1.23. And then 0.74. Hopefully I'm doing this correctly. Actually, college and not work. I just want to make sure that adds up correctly. 67. That should be fine. And then 1.23 minus 0.74. We get negative 0.49. I think I must have misadded something, so not work. Give me 1 second while I just figure out what did I not. Oh, it's 0.8. That's what it is. Sorry. So this should be 0.75. 5, which then would make it 4.8. And then we get the probability of C and not W equal to 0.48. So that's how you would figure it out. Unfortunately, I think it requires more work using the formula for that one. So this is a case where the Venn diagram is better. Okay. And again, there could be another way of doing it too. Like this isn't, that's the thing about probability. Sometimes there's more than like 4 or 5 ways of doing the exact same problem. And you just kind of have to figure out, well, which is the best one. All right, last question for this type of problem is what percentage were neither in college nor work, right? So this problem is a really good example of the complement rule, okay? So this is a very good example of the complement rule because really the probability of not work or college is equal to 1 minus the probability of both college or work, right? I guess it'd be and work. So the opposite. Give me 1 sec. Correction, it was 4. I was right. The opposite of nor is or, so the opposite of or is and, but the opposite of nor is or. Like, don't worry about that. That's not a big deal, but for me, I just want to make sure I said that correctly. Neither. All right, and then so 1 minus both college or work. If you read back here, 92% were in college or working. So 1 minus 0.92 is equal to 0.08. And there it is. Or again, if you look at the Venn diagram, the neither would have been 0.08 right there if you added those up. Okay. Small correction if you're actually watching the video. This should have been 0.25. I'm sure if you're watching earlier and working along, you would recognize that. But I don't think I used it at any point, so. Nope, didn't really use it besides writing into the Venn diagram. So that should have been 0.25. And then now that's where I got, so that's why I got 0.07 last time in my head. So now we're good. Any questions on that? So the last section we have to cover is marble problem, just combinations. It's basically using combinations and probability. I will say this because I mean, it'd be kind of dumb for them not to do that. There will be at least one marble problem on the exam because we have one whole section covering it. So it could be one of the, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9 problems. There's like 9 problems that they give you. And they could probably ask you 1 or 2 of them. Okay. But there will be at least one marble problem because otherwise there would be no point in covering section 8.4. So practice the marble problems. Like that's like the only problem that I can guarantee you will be on the exam because there's a whole section on just doing this problem, right? So when you're doing a problem like this, it's all about just figuring out what's your total and what you want, right? That's all you got to think about it. So step 1, okay, is to define your event. Define your event. So they said all green. So I want the probability. So actually, my event E will be all green. Okay. That's the first thing you want to do. Step 2, how big is your draw? So how many are you drawing? Because that's going to be the number that you use for the total. So there are 4. 4 are drawn. So 4. Step 3, find, formula. So the probability of whatever you want is going to be the number of what you want over the number of the total. Okay. Number of all green over total. Step 4 is find total. Find the total first, every single time. So when you're drawing marbles, you don't care about the order because that's not what matters. What matters is how many you have of each of them, right? So I am drawing 4. Okay. Sorry, incorrect. I got to count the total number of marbles. So there are 5 red plus 6 green plus 4 blue. And if I add those together, I get 15 marbles. Okay. And what I am doing is I am grabbing 4 of them all at once. Okay. Not one at a time, but all at once. So I have 15 marbles and I am choosing 4 of them. Okay. So 15 choose 4. And that's my total. And if you want to write this as a number, right? It's going to be 1365. 1365. And then step 5 is to find your event amount. So I want all green. So this is where you kind of have to think about it logically. Well, you want 4 marbles total. Like when you're drawing, you're grabbing 4 marbles. So how many green do I have? I have 6 green, right? Which means 4 of them have to be green. So I have 6 green and I am choosing 4. Have I drawn all 4 marbles? Yes, that's it. That's all we have. 6 choose 4. All 4 marbles are green. And then step 6 is plug in. And if you do 6 choose 4 in your calculator, 6 choose 4, it's 15. So the probability of all green is equal to 15 scenarios where I draw 4 green marbles out of 1365. And if I plug that into my calculator, hit math frac, then the answer will reduce to 1/91. So to do the combination on your calculator, you hit, first type in the total number, so 15. Hit the math button. Now, if you have a newer calculator, you have 5 options on the top. If you have an older one, you only have 4, but for all of them, it's PRB. PRB. And then you go to NCR because you're choosing, not permuting. And then you're picking 4 marbles. And there it is. And then for the other one, I have 6 green, math, PRB, NCR, 4. Okay. And then 15 divided by 1365, hit the math button, do frac, and then 1/91. If you want to do the combination as a fraction, you can just put parentheses around it. I wouldn't recommend doing that. I would do them separately. Combinations are always nice numbers. So to me, it's not worth the headache of doing them all in one shot. Just do it one at a time. Okay. All right, let's go to the next example. So the next one says, are all the same color? So it's the same principle, right? Step 1 is define your event. And so this is going to be all same color. So here's the problem with this one specifically. If you want to do all of the same color, you're going to have to do multiple scenarios, basically when they're all red or they're all green and they're all blue, and then you're going to have to add them up together. So this is one of the cases where it's actually better sometimes to do the complement, but we'll see how it works out for us. So step 1 is they're all the same color. Step 2 is formula. So the probability of E is equal to the number of E over the number of the total. So step 3 is to find total. So you're still drawing 4 marbles. So 4 marbles. So I still have 15 choose 4, right? That has not changed. It's still 15 choose 4 and 1365. Okay. So with a problem like this, you're just going to keep repeating the total for basically all of them. So that's where we're going. Okay. And so for this one, step 4, let's write it up here, is to find E. So you're going to find the number of E. So here's the thing. If you draw all red marbles, you also can't draw blue marbles, right? If you draw all blue marbles, you can't draw red or green, right? So these are all exclusive events. So we're going to add them together. So if we do all red, well, how many ways can we do that? Well, according to the problem, we have 5 reds. So 5 choosing 4. Okay. And then for all blue, if we look up, we have 4 blue. So 4 blues, and we're choosing all 4 of them. And then for all green, if we look up, we have 6 of them, and we're choosing 4, right? And if I plug this into my calculator, 5 choose 4, 4 choose 4. Whenever you have something like 4 choose 4, that's always 1. And then for 5 choose 4, I'll do that right here just to practice one more time. So 5 math, BRB, sorry, NCR, 4, 5. And then if you're gonna be doing this multiple times, you could do second entry, and then now you could just modify it. So 6 choose 4, and I get 15. And so because each color is exclusive, can't draw 2 colors. In this case, add them. So 5 plus 1 plus 15 is equal to 21. And then step 5 is plug in. So 21, the probability of E is 21 over 1365, which is 1 over 65. This one is probably one of the more challenging ones because of the fact that you kind of have to think about it a little bit differently. So I understand if that one's a little bit more challenging. It's just the nature of that problem specifically. All right, let's do the next one. At least 3 red. Okay. Again, still the same scenarios. It's still the same number of marbles, 5 red, 6 green, 4 blue. We're still drawing 4 marbles, right? None of that's going to change for any of these, but I'll keep reminding you that it's at least 4 marbles. So step 1, define E. So the probability, sorry, not probability, E. You don't have to do this step. This is just something that I do to myself so that I remember. At least 3 red. Step 2 is formula. So the probability of at least 3 reds is the number of times you can get at least 3 reds over the number of the total. Again, the bottom is always the total. Step 3, what is the total? So I have 15 marbles. I am choosing 4 of them. So that's still 1365. Again, that's going to be the same for all of them. And then step 4 is the one where it changes. So the number of E. So this is where it's at least more interesting because you have to think of all the different cases that you can do. So it has to be at least 3 red, right? So it's either 3 red or 4 red. Okay. So that means, again, you have 2 different situations. So you're going to have to add them together. So one of them is 3 red, and then the other one is 4 red. Okay, so you have to look at both cases. So if it's 3 red, then how many reds do I have? I have 5 reds. So 5, choose 3. Okay, that covers all of my 3 red marbles. But then I still have to pick one more marble because I have 4. So how many do I have left? Well, 6 plus 4 is 10. So I have 10 marbles and I'm choosing 1. So again, this right here is 3 red. And then this is just one more to have 4. And the reason you're not including the red marble that's still left over is because if you did, then you would have 4 red marbles, and that's not what you want, right? So that last red one, or the 2 red marbles that are still left, you can't use them anymore. And then for 4 red, it would be, well, I have 5 red marbles and I'm choosing all 4 of them. So that's it. And so if you plug this into your calculator, so 5, choose 3. 5, choose 3. We get 10. And then whenever it's 10, choose 1, or a number choose 1, it's just whatever number's in front. So it's 10. 10 choose 1 is 10. Actually, yes, 10 choose 1 is 10. And then that's 100. And then 5 choose 4. I think we did that one earlier. 5. So then we just add them together. So adding 100 plus 5 is 105. And then step 5 is to plug in. So the probability of E is 105 over 1365. And if I plug that into my calculator, 105 divided by 1365, math, frac, 1 over 13. Like that. All right, so we go on to the next one. Again, what makes these challenging is the more restricted they become, the more considerations that you have to make. So that's where we're going to be. They're always pulling out at once because if you're doing one at a time and you're keeping track of the color, that's a different problem. That's actually 8.5, and we call that conditional probability. Because if you draw a marble and you know what color it is, what's it called? If you don't put it back in the bag, that changes all of the probability. If you put it back in the bag, then that also, it doesn't change like the sample size, but it changes basically how you would calculate, use multiplication rule. So we don't have to worry about that. Yeah, that's going to be an 8.5 thing. Okay. Again, step 1 is define E, your event. So my event is 2 blue and 2 other. Okay. Step 2, what is the formula? So the formula is the probability of E equal to the number of E over the number of the total. Step 3, okay, what is the total? Again, we're still drawing 4 marbles out of 15, so 15 choose 4, 1365. It's going to be the same total for all of them. And then step 4 is to find the number of E, N of E. So I need 2 blue. Okay, so 2 blue. Well, how many blues do I have? I have 4 blues, so 4 choose 2. That covers my 2 blue marbles, okay? And so that means I have 11 marbles left. So that means I have 11 left, and I don't care. So I do care. It has to be one of each of the other colors, which means the next one, it doesn't matter if it's red or green. It's just if it is red, the next one has to be green. And then if it's green, it has to be red. But because we don't care about order, it doesn't matter which one comes first. So let's just do the reds first. So how many reds do I have? I have 5. And I need 1 of them. And then I need green. So how many greens do I have? I have 6. And I need 1 of them. Now, if I said something like 2 blues and then just 2 more marbles, then it would be like, well, how many do I have? 11 of them, and I would just need 2 of them. But because I specified the color, like I need 1 of each, then I have to be more specific. So if I do 4 choose 2, So 6. 5 choose 1 is 5. 6 choose 1 is 6. Remember, if you see a number C1, it's just a number at the very front. So 180. And then step 5 is to plug in. 180 over 1365. 180 divided by 1365. If I do math frac, 12 over 91. And there you go. All right, so the final example of this type, and this one is really, really a big one, because if you don't use the complement rule, then you would have to basically add up every single scenario, meaning you would have to do when it's 1 green, when it's 2 green, when it's 3 green, when it's 4 green, and when it's 5 green. So the probability of not being all green, okay, would be the sum of it being 1 green, 2 green, 3 green, 4 green, or 0 green. Like there's no greens, right? And you have to add those all up, okay? So for this one, step 1 is we're going to define E. So E will be equal to, and this is where I tell students, I always recommend that you write your events, no matter what they tell you, as a positive statement. So I am going to define it as all green, which means the complement of that is not all green, right? So for this one, we're going to do our formula. The probability of not green, which is what we want, is 1 minus the probability that they are all green. So I only have to look at one scenario when they're all green, not when it's 0, 1, 2, 3, 4, 5, because I think there were 6 of them, right? Yeah, you'd have to look at 6 different cases, 0, 1, 2, 3, 4, 5. And this is probably the most challenging one because of that. So step 3 is to find total. Again, total still the same. I have 15 marbles and I'm still choosing 4, right? So we're still doing 4 marbles. And from there, we get 1365. Step 4 is to find the number of E when they're all green, because this is the one that I need to find. So if E is all green, so how many marbles do I have that are green? 6. And how many do I need to make them all green? So this is all green. So 6 choose 4. I think we did that earlier, but I don't remember it. 15. And so step 5 is to plug in. So the probability of not all green is equal to 1 minus 15 over 1365. And if I plug that into my calculator, 1 minus 15 divided by 1365, math frac, I get 90 over 91. And I'm done. So that one is a little bit more challenging because you have to use the complement to make your life a lot easier. All right, I'm going to do one more because this was on the homework and they don't do an example of this exactly on any of the 2. So I just want you to at least have one example of this type. So this is a bonus one. That was E, so F. Exactly 2 green marbles. Okay. So we're going to do exactly 2 green marbles. So again, step 1 is define E. E is equal to 2 green. Step 2, formula. The probability of E is the number of E over the total. Step 3 is to find total. So what is the total? The total is, well, I'm still doing 15 marbles and I'm still choosing 4. Again, 4 marbles. And so that's 1365. Okay. And then step 4 is going to be find number of E. So I need exactly 2 green. So I have 6 green and I am choosing 2. 6, choose 2. Okay, so this is 2 green. And then I just need 2 more marbles. So if I go back to the very beginning, how many marbles do I have? I have a total of 15. 6 are green, 5 are red, and 4 are blue. So then that means I have 9 marbles left, and I just need 2 of them. So 2 more, not green. So red plus blue. And if I plug that into my calculator, 6 choose 2. That's going to be 15. And then 9 choose 2. 36. And so 15 times 36, 540. And then step 5 is to plug in. 540 over 1365. And then math, frac, and 36 over 91. So if I ask you for exactly like 4 red or 3 red, you just basically find the combination of grabbing those ones first, and then whatever's left over, you just fill in with how many you still need to make the entire hand. Okay. Okay, so I'm just gonna rapid fire through these ones just to, it's the same problem, right? Nothing has changed. So the first thing is, what's the total? Well, the total is 4 plus 3 plus 2 plus 1. So that's going to be equal to 10. So you have 10 marbles. And then you're grabbing, sorry, your hand is equal to 5. Okay. So find the probability she has all the red ones. Okay. So E is equal to all red. So then the probability of E is equal to the number of all red over the total. So the total is I need 10 marbles and I'm choosing 5 of them. So 10 choose 5. That's going to be the total for all of them. And then how many red marbles do I have? I have 4 red marbles. How many am I grabbing? I have 4 of them. But I still need 1 more marble to fill out my entire hand. So how many do I have left over? I have 6 of them, and I just need 1 more. Okay. So 4 choose 4 times 6 choose 6. If you plug that into your calculator, you're going to get 6. And then 10 choose 5. If we do 10 choose 5. Uh, 252. So these are all going to be 252. And if you simplify that, 6 divided by 252, math frac, 1 over 42. Okay. And there it is, 1 over 42. For the next one, at least 1 white. So the probability of at least 1 white. So this is where the complement rule is better, because if I do at least 1 of the white marbles, I'd have to look at the case of just 1 white marble or 2 white marbles. So you could also rewrite this as 1 minus the probability of no white marbles. And that will be a lot less work. At least statements or nor more than statements, you have to cover every single case and add them all up. But often you can use the complement to basically look at the opposite problem where there's only 1 case, and that makes your life a lot easier. So then this is going to be equal to 1 minus, I'm still having 10 marbles and I'm choosing 5 of them. If I don't want any white marbles, well, I just have 8 marbles left and I am choosing 5 of them because there are 2 whites and I don't want them here. So let's get rid of them. And so if I plug that into my calculator, I get 252, and then 8 choose 5 is 56. So 1 minus 56 divided by 252. And then if I hit the math frac button, 7/9. And that matches the answer. Okay. So again, this right here means no white marble. Okay. So, or you can do it as the probability of at least one white marble is equal to probability of 1 plus the probability of 2. And then you'd have to look at both cases and add them up. Again, personal preference if you prefer to do the direct statement versus the other statement. And then we have 2 more. So 2 red and 1 of each of the other colors, and she does not have all the red ones. Okay. So again, still the same colors and totals and everything. I'm just grabbing this to make sure we have it next to it. Should have done the last step, but that's okay. So 2 red and 1 of each of the other colors. So probability of 2 red and 2 other, and 1 of each of the others. So this one's going to be a little bit more interesting. I'll just put more. So that's going to be equal to, so we're going to do the total. And then the number of 2 red and 1 of each. So I need 2 red marbles. So I got 4 red and I'm choosing 2 of them. That's my reds. And then I got 3 green and I'm choosing 1 of them. I have 2 white marbles and I'm choosing 1 of them. And I got 1 purple and I'm choosing 1 of them, right? Let me give myself more space. So this is red, green, white, and purple. And then the total is still 10 choose 5. And so if I plug that into my calculator, I just got to do 4 choose 2. I'm sure it's like 6 or something, but I don't remember. Yep, 6. 6, and then 3 choose 1 is 3, 2 choose 1 is 2, 1 choose 1 is 1, over 252. And so I get 36 divided by 252. Math frac, 1/7, like that. And let's just verify that answer is correct. Yep, 1/7. And then she does not have all the red ones. Okay. So basically, if she doesn't have all the red ones, that means she has either 0 red, 1 red, 2 red, 3 red, but 4 red would not be allowed. So again, this is another case of the complement, the probability of not all red is equal to 1 minus the probability of all red. So that would be 1 minus, the only time you can have all red is if you have 4 choose 4 for the red marble, and then you just need a 5th marble, so that gives you 6 choose 1 more, and then we're still doing 10 choose 5. And then this is going to be equal to 1 minus 6 over 256, which is equal to, according to my calculator, 1 minus 6 divided by 256. Math frac. And 125 over 128. But I think I... Four choose 1. Not all red, 1 minus the red, so... And then I read 1, 1. Did I type that incorrectly? Sorry, it's 252, not 256, so then it's 41 over 42. Yep, that was my mistake. It's 1 minus 6 divided by 252. Math frac. There we go, 41 over 42. And we got it. And that's all the examples for probability.